You buy an apple pie from a local business owner, they put it in the microwave, and then they hand it to you. Which bit are you worried might burn you? Which bit? Is it the cardboard wrapper or the pastry or the filling or all of them? It's the filling, isn't it? Why is the filling so hot and the pastry not? That's the kind of thing we're talking about today, chums. Hello, I am Lara. This is Theatre Science. I'm trained to teach physics up to A level, and now we're just doing free live lessons into the internet. And today we're doing specific heat capacity. Now, I'm a physics teacher, right? So I love all of physics equally, but specific heat capacity, like, it's a tough combination of words to fall in love with, isn't it? Heat's okay, but specific capacity. Let's try and make this a little bit more interesting, okay? I said to bring 2 glasses of water with you. What I'd like you to do is to put one of those glasses of water aside, and we'll deal with it later. Can you hold... Well, you don't have to hold it. I'm just holding it because it's better telly. You need a glass of water and a metal spoon for this first activity. I want you to imagine, right, that you're a detective and there's a crime being committed in a room, and you and your partner burst into the room, and the criminal leaves out the window, and your partner follows the criminal and chases them, and you're left at the scene of the crime, and you have to investigate, and you come over to the table. And I'll tell you what, I forgot. Can you please put your hand into the glass of water? I know, you might not want to. I mean, you don't have to if you don't want to. It's a bit unpleasant. It's quite chilly. And with the other hand, can you hold the spoony end of the metal spoon as well? Okay, cool. Thank you for learning reasons. Hold the spoony end of the metal spoon in one hand and put your hand into the glass of water with the other hand. Yeah, you come to the table, and there's a spoon on the table, and there's a glass of water on the table, and it's up to you to decide, to determine, to work out as the detective whether the criminal has touched the spoon or the glass of water. Okay, very important information, must be gathered. So what you do is you touch the spoon and you touch the glass of water. Can you work it out? Can you work out from just touching the spoon and touching the glass of water, like putting your hand in the water, taking the temperature of the things, whether the criminal has touched them or not? When I taught this lesson a couple of years ago on Facebook, everyone started going off in the comments about what kind of crime you could possibly do with a glass of water and a spoon. Shh! Doesn't matter, okay? Let's focus on the task at hand. We're learning about specific heat capacity. Can you now put your metal spoon and you take your hand out of your glass of water? I should have said to bring a towel or something, right? Dry your hands. Rub your hands together, because to make it a fair test, really, they need to be the same temperature. I think that'll do. Can you touch your spoon again? Can you tell that you've been holding it? A good way to tell, I suppose, is to touch the bit of the spoon that you weren't holding, and then touch the spoony end of the spoon. For me, straight away, the spoony end of the spoon is warmer. I can tell someone's had their hand on this spoon. The temperature of that bit is very different to the temperature of that bit. Heat is conducted from someone's hand into the spoon. Can you do the same with a glass of water? If you put your hand in a glass of water, can you tell someone's had their hand in that? You can't, can you, chums? Why not? I hear you cry. Well, the answer is specific heat capacity. I will read you the description of specific heat capacity, which is the description you have to write if an IGCSE exam ever says to you, what is specific heat capacity? Okay, here it is. You ready? Yeah, let's go. The specific heat capacity of a material, that's stuff like water or copper or whatever. The specific heat capacity of a material is the amount of energy required to raise the temperature of 1 kilogram of the material by 1 degree C. Will it help your understanding if I say it again, but with some stuff underlined in pink? The specific heat capacity of a material is the amount of energy required to raise the temperature of 1 kilogram of the stuff by 1 degree C. Basically, the specific heat capacity of a thing is how much energy you have to put into the thing to make it hotter. Right? That's all it is, really. How much energy you have to put into the thing to make it hotter. So, specific heat capacity, it sounds awful, right? But it really does relate in interesting ways to everyday life. Like, you possibly know that in the summertime, land gets hot quite fast, right? Nice, beautiful, bright summer's day, sun shines onto the land gets warm. If you go to the seaside, you're like, yeah, beautiful, summer's day, into the sea. If you live in North Yorkshire, where I am, in the UK, you go into the sea, you very quickly find out that the sea is a very different temperature than the land. The sun is still shining on the sea, but the sea is not heating up at the same rate as the land is. The land is nice and warm. The sea is going to take a lot longer to heat up. And actually, in the wintertime, the land has very quickly cooled down, but the sea, it has finally got up to temperature and is now quite warm because it takes a long time to cool down. So that's specific heat capacity. You get a kilogram of stuff, all right? I'm miming to help your understanding. Get a kilogram of stuff. The specific heat capacity of the stuff is how much energy you have to put into the stuff to make it 1 degree hotter. Okay? All right. So if I got some seawater, you have to put loads and loads and loads of energy into seawater, into like 1 kilogram of seawater to make it 1 degree warmer. Whereas you get some land, you don't have to put much energy in, the land's just, pew, it's hotter. All right? Okay, let's check if you've understood. You've got your glass of water, hopefully, and your spoon still. Which one of these has the highest specific heat capacity? Now, that wasn't a very well worded question, was it? Because a spoon isn't a material. It's steel, say. What has the highest, let's just call it metal. Which one of these has the highest specific heat capacity? Metal or water? Which one of these has the highest specific heat capacity? Metal or water? I'm really happy with this question because on Facebook, it was brilliant. People were like 50-50. Half of the people were saying one thing, half the people were doing the thing. And people were doing the thing that I love as a teacher when they go, water, no, metal, no, water, because it really shows that they're not looking it up, like they're properly thinking. Have you got an answer? I'll give you this description again because we need to get it into our brains, don't we? The specific heat capacity of a material is the amount of energy required, the amount of energy you have to put into a thing to raise the temperature of 1 kilogram of the material by 1 degree C. Okay, well, it's the metal. The amount of energy, the amount of energy required to raise it, it's the water. The water has the highest specific heat capacity. You've got to put loads and loads of energy into water to increase the temperature, even a tiny little bit. The metal, you barely touch the metal and it heats up. Phew, it's so easy to heat up metal. You hardly put any energy in. You just rub a tiny bit of energy on it. That's not science. And it immediately heats up. Whereas water has a very high specific heat capacity. You have to put a lot of energy in, a big amount of energy to increase the temperature of water by 1 degree. And in fact, water is the sort of material that you encounter that will have the highest specific heat capacity, probably. Okay, some of you will be absolutely delighted and some of you will be mortified to learn there is an equation for specific heat capacity. Here it is. That's a good one. Specific heat capacity equals energy equals mass times specific heat capacity times the temperature change. We'll have a little bit of a practice at this, so don't worry too much if you don't get it at all. Hopefully you'll get it a bit by the end. Energy equals mass times specific heat capacity times temperature change. If that's confused you, you'll be happy to know that we can just do it in symbols. So it's actually change in energy, really, because it's the amount of energy that's gone in, or maybe it's the amount of energy that's gone out if the thing's cooling down. Change in energy, this lovely little delta triangle, meaning change in, E equals M for mass, times C for specific heat capacity, times delta theta, which means temperature change. And if you're like, oh, that looks too pleasant, Lara, okay, fine. You can have it like this. Change in E equals MC change in theta, because if you don't have anything in between the letters, it means you're timesing them, right? Right? Is that okay? Yeah? Okay. So one of the things you're going to have to do if you do an IGCSE physics exam, probably, is to rearrange an equation. So I always complain about how hard it is to teach maths in this format, because some of you will have done loads of maths already, will be very well practiced with maths, and some of you might be only just starting out on your maths journey. So you'll all be in different places. Some of you will find this really easy, and some of you will just not have done it yet and won't be able to do it. I've asked you to rearrange the equation to make m and c and change in theta the subject. I am going to very quickly show you how I check my working when I rearrange equations, just in case that helps, at the risk of boring some of you who already know how to do it. I'll give you a couple of seconds and then I'll show you what I do. Okay. Right, I'm gonna show you. Some of you will be like, "Oh, I already know how to rearrange equations. Get on with it. Give me some cool maths." But sorry, we have to get everyone on board, don't we? We just have to. Here we go. I'm gonna flip you around. Hello. So, a lot of you on Facebook the other day were getting a bit scared by the letters. Let's just do really simple numbers, right? So far, if I'm thinking about how to rearrange equations, and I would still do this, to be honest, if I was in an IGCSE physics exam, because you never aren't you, and the clock's ticking, and it's always good to have ways to check how you rearrange equations. I'll tell you what, for the first, let's just do 6 equals 3 times 2. If I want to rearrange that to make it 2 equals whatever, how do I do that? Well, I want 2 on its own. I want 2 to be on this side on its own, because it'll say 2 equals blah, blah, blah. So I need to get rid of this 3. And the rule for rearranging equations is, whatever you're doing on one side, you have to do the opposite on the other side. If I just teach you this and then you have a tiny little practice and that's all the maths you do this lesson, I'm so happy with you. So we need to get rid of this 3, and it's times 3. So when we move it over to this side, we're going to say divide, okay? So we just get rid of that, say that that's not there anymore, move the 3 over here, but because we times on that side, we do the opposite on this side, so we divide. And that's it. You've changed it into 6 divided by 3 equals 2. And you can check that in your head, can't you, quite easily? 6 divided by 3 does equal 2. Hooray! So, if I was rearranging this equation to make m the subject, for example, then I'll do the same again, right? In fact, you can be a bit faster with this. Change in E equals m times c times change in theta. If I want to get m on its own, I'm timesing both of these. It's c times change in theta. So because that's all times, like times there and times there, I can just take that whole thing and divide it on this side. So to rearrange this equation, I would say, can I do it up there? Have I got room? Not really. To rearrange this equation, I would say m, I'll do it like this, m equals change in E, but then it's all times on that side, so I'm going to divide it on that side. Or if you're really unhappy with this, you want to do it in bits, you can. I want to get m on its own, so I'll get rid of this c, and I'll move it over here, divide by c, but I'm also timesing by change in theta, so I'll move that over here as well, and times by change in theta. Phew! Okay, I've got change in E divided by c times change in theta equals m. And I can check if that's right, okay? Oh, I wish I hadn't rubbed all this out. I can check if it's right by just using my simple little numbers again. So let's say that change in E is 6, and that m is a 3, and that c is a 2, and let's just say that's a 1. That's correct, isn't it? 6 equals 3 times 2 times 1. Cool. Now I'll rearrange it so that I've made this thing. So I've said 3 equals 6 divided by c is 2, and change in delta is 1. So what I'm saying with those rearranged numbers is 3 equals 6 divided by 1 times 2. And that's right, isn't it? 6 divided by 2 times 1 does equal 3. Phew! So, I mean, for some of you that will be really laborious and you just won't feel like you need to do that. But for me, plugging in really simple numbers and knowing that it works is a nice way to stop me panicking in the middle of an IGCSE exam. Sorry, I'll put you in front of the questions. Here you go. So have a go at those. So we've already done M, actually. So have a go at the other two. I like this lesson because there's some maths at the start, and then we get into a bit of, well, I don't know what you'd call it really, like looking at words. So there's something for everybody. We get to exercise our brains in different ways. So some of you will be fine with this. For some of you, if you want C on its own, you want C on its own, so you've got to get rid of M and you've got to get rid of changing theta, and your times in them on this side. So when you put them over there, what have you got to do? I won't give you too long, because I think it's one of these things where if you know how to do it, you do, and if you don't, you probably want to practice it on your own time without me rushing you. All right, so what we end up getting, and I'm not going to ask you to do this during the questions, I've already rearranged them for you when I give you the questions, is C equals change in E divided by M times change in theta. And change in theta equals change in E divided by M times C. Phew. Right. I'd like you to have a little practice with that. So I've got a couple of maths questions for you, but I have rearranged the equations for you already. To see how you get on with those. Again, if you're not comfortable with maths, if you just spend the next 3 minutes staring at question 1 and really try and don't get it right, and then watch me go through the answer, that's great. You do you, okay? After this, we'll do a sort of written activity. I'll show you how you actually work out the specific heat capacity of things. And then I've got like a really fun, tricksy puzzle for you, which. So here we go. Have a go at these questions, right? I've given you the specific heat capacity of water. It's 4,200 joules per kilogram degrees C. Be a bit careful here. You're going to keep wanting to write joules per kilograms per degree C, because it doesn't sound right saying kilogram degree C, but that's what it is. The equation tells us that the units for mass and specific heat capacity, if you do the equation, it pops out that the units for mass and temperature just need to be next to each other like that. You're timesing mass and temperature. You're not dividing them. And the specific heat capacity of aluminium is 880 joules per kilogram degree C. So your first questions, you don't need to rearrange any equations for these. I just want you to plug in the numbers. How much energy do you need to raise the temperature of 2 kilograms of water by 1 degree C? Okay, how much energy do you need? So what is, you can say, if it's just how much energy you need, that's fine, that's change in E. How much energy do you need to raise the temperature of 1 kilogram, so that's your mass, of water, so that's the specific heat capacity, that's C for water, by 1 degree C, so change in theta is 1, okay? How much energy do you need to raise the temperature of 5 kilograms of water by 0.8 degrees C? So exactly the same equation, but it's 5 kilograms and it's 0.8 degrees C is the change in temperature. And 300 grams of water by 4 degrees C. What have I done? Gasp, I'm trying to catch you out. What? It says grams, but it needs to be kilograms. How are you going to change grams into kilograms? You've got to divide it by 1,000, don't you? Anyway. Question 4. How much energy does a 3 kilogram block of aluminium lose when it cools from 200 degrees to 50 degrees? Be careful, that's aluminium, not water. And question number 5, a pan contains 0.5 kilograms of water at 6 degrees. 3,150 joules of thermal energy, that's just energy, shifts to the water. What is its temperature afterwards? A pan contains 0.5 kilograms of water at 6 degrees C. 3,150 joules of thermal energy shifts to the water. What is its temperature afterwards? That one is designed to be quite hard because obviously some of you will be comfortable with maths and will need something else to do. be really careful with your units, please. I should say, like and subscribe. And if you're watching this on YouTube live, you'll notice there's no comments on YouTube. But as usual, over on my Facebook page, I have put up a post saying that you can comment on that post if you like, and I will read them out and say hello to you at the end. Hello, Orin. You already said you were coming, didn't you? So I'll say hello to you right now. Kind of lost track of time because I was listening to the birds outside my window and trying not to talk to you. How are you getting on? I think I've been really thoughtful and left the questions on the board so that they'll be there even when I go through the answers to the first ones. Should we have a look? Should we push down on the PowerPoint and see? Oh, look at that. Well done, me. I'll go through the first 3 questions, but I'll leave those other 2 on the board for the people who are just finishing off. How much energy do you need to raise the temperature of 2 kilograms of water by 1 degree? Well, you just do energy equals, don't be too scared of the delta, the change in sign. Energy equals, and then plug the stuff in. So energy equals mass times specific heat capacity times change in temperature. It's only change in temperature by 1 degree, so you can sort of ignore that, can't you? It's just 2 times 4,200 joules per kilogram degree C. So the answer is 8,400 joules. Phew. So if you're still finishing off these ones, you can just tick or cross 8,400 joules, right? Or write it in. So the second one was exactly the same, wasn't it? Except the numbers were a bit different. So it was energy equals 5 kilograms times 4,200 joules per kilogram degree C times 0.8 degrees C. So you should have got 16,800 joules for that one. And I'm just going to be a bit annoying, I think, and bang on to you like I always do about how you're going to check that answer, do you know? Especially if we're rearranging equations like this. This is a great opportunity for me to bang on, as I love to do, about how you should always check your answer. Oops. We'll go through the third one first, though. Oh, I was a bit sneaky, wasn't I? 300 grams of water. So you need to know that there's 1,000 grams in 1 kilogram. So 300 grams of water is 0.3 kilograms. It's like roughly a third of a kilogram, isn't it? So that was 0.3 kilograms. You had to convert that times 4,200 joules per kilogram degree C times 4 degrees C. And the answer was 5,004 joules. So the thing I want to bang on about is you can always check your answer by looking at the units, yeah? We've talked about this quite a few times. So energy is measured in joules. Whatever you do to the units, whatever you do to the numbers, you have to do to the units as well. So if we've written kilograms times joules divided by kilograms times degree C times degree C, we need joules to pop out of there because energy is measured in joules. Instead of just plugging in the numbers to your calculator, getting an answer and then going, oh, well, I was looking for energy, so I'll just write joules on the end because energy is measured in joules. Why not write down what you're doing with the units in it and then check if you got it right. Check that you've rearranged your equation properly. So I've written this in a weird way. Instead of writing like / kilogram degree C, I've written the proper divided by sign because I think that makes it easier to see. Are you all okay with the fact that like 20 divided by 20 is 1, and a gabillion divided by a gabillion is 1. If you've got something on the top and the same thing on the bottom, then it just cancels out. Well, if you're not, then that's what I'm telling you. It does. So if we look at just the units here, if we ignore the numbers, what have we got? We've got a kilogram on the top there, because you can just kind of imagine this is all extended. If you don't know this, then, I don't know, you might want to have some fun on BBC Bite Size looking at fractions and rearranging equations. But anyway, you can extend that line across. That's all the being times by, and that's the divided by. So I've got kilograms up there and kilograms down there, so those cancel out. And look, I've got degrees C up there and degrees C down there, so they cancel out as well. So I am left with joules. So again, if I was in an IGCSE exam, I'd definitely be doing that, because this is a brilliant sign that I've rearranged my equation correctly, because I've got energy equals something measured in joules, which is what it is. Okay, moving on. How much energy does a 3 kilogram block of aluminium lose when it cools from 200 degrees C to 50 degrees C? So yes, specific heat capacity doesn't just have to be about stuff heating up. It can be about it cooling down. We've got a change in temperature here, haven't we? It's gone from 200 to 50. So the change in temperature is 150 degrees C. And then you plug that into the equation, remembering that you're suddenly talking about aluminium and not specific heat and not water, so it's a different specific heat capacity. So the answer you got if you plugged all that in was 396,000 joules. 396,000 joules. I was quite pleased with how sneaky this last question was. A lot of people getting very confused, especially 2 years ago, actually, when I taught this on Facebook. A lot of people confused by that. Have you got that? 396,000 joules. Can we move on to question 5? Oh, excuse me. Okay, here we go. A pan has got half a kilogram of water in it. It's 6 degrees C. 3,150 joules of energy sort of goes into the water, shifts to the water. What's its temperature afterwards? Well, we've got change in temperature equals change in energy divided by mass times specific heat capacity. So let's plug in the numbers. That's how much energy went in, divided by the mass, times the specific heat capacity of water. So the answer is 1.5 degrees C. Now, a lot of people on Facebook were very confused by their answer, which was 1.5 degrees C, and were like, why is the water cooled down? What? It's on a hob. It's 6 degrees. Energy gets put into it, and now it's 1.5 degrees C. And I said, well, why has the water cooled down? And they all started saying, not all of them, but a couple of people said, like, oh, because we've just done evaporation. Like, if you're stirring it, more water particles are going to evaporate, and that's going to cool it down. And I was like, no, you've got to think about your everyday experience as well. If you're heating something on a hob, if you stir it, it doesn't cool down, does it? But it's a very good idea to read through the question and the answer and see if that actually does make sense. It doesn't make sense, does it, what we've got there? And that's because that is not the answer. That's the change in temperature, which isn't quite the question. They haven't said how much hotter is the water by the time the energy's gone into it. They've said, what is its temperature afterwards? So if it was 6 degrees and now it's gone up by 1.5 degrees, you've got to add those together. And its temperature afterwards is 7.5 degrees. Makes so much sense. Okay, so one of the things that you need to know about, not actually do, but know about for IGCSE physics, is how to actually work out the specific heat capacity of some stuff. So I'm going to talk you through how you do it. And then when I sort of read about it myself, I had some questions and I thought, oh, I'll ask them those questions because you might be interested and it might help you get some marks or whatever. And then I'll go through the answers with you. Okay, so here is my quick PowerPoint about how you find the specific heat capacity of aluminium. Are you ready? Okay, good. Experiment to find the specific heat capacity. Oh, sorry, a bit wobbly. The Lego phone holder's a little bit out of joint. Let's give it a. There we go. That's better, isn't it? Oh, it's also expensive back here. Here we go. So first thing you've got to do is take the mass of the 1 kilogram aluminium block using a balance. Okay, so the experiment requires a 1 kilogram aluminium block. The first thing you do, it's so hard to not say weigh it. So hard, but you're not weighing it, are you? Remember our previous physics lessons, if you came to them, weight and mass are a totally different thing. We haven't mentioned weight once, have we, in this lesson about specific heat capacity? So you need to take the mass, because kilogram is a measure of mass. Take the mass of the aluminium block using a balance. I know they're scales, but we're doing physics, so we need to start saying that it's a balance. Scales measure the weight of things, a balance measures the mass of things. Okay. So you've got the mass of your 1 kilogram block of aluminium. Next thing you have to do is put an immersion heater, which isn't plugged in, into the block, okay, into one of the holes, because it's a special physics block of aluminium. It has 2 holes. Immersion heater goes into one hole, thermometer goes into the other hole, and you record the temperature, okay? So that's before the immersion heater's on. Literally just take the temperature off the block of aluminium, and then you wrap the block in insulating material. How are you going to work out how much energy goes in? You need to have watched the electricity module for this. We won't go into it too much, but if you take the current which is flowing through the immersion heater, and you know the voltage across it, and you can measure those quite easily, and then you connect it to a power supply and turn it on, then you will know how much energy, you can calculate how much energy is going in. So you let the aluminium block heat up for 10 minutes, and then at the end of the 10 minutes, you write down the ammeter and the voltmeter readings. When you've switched the heater off, the block will get a little bit hotter after that. So just keep watching the thermometer, wait until it's got to its highest temperature, and write that down. And Bob's your uncle. You've got the current and the voltage and the time, so you can work out how much energy went into the block. And you've got the temperature change, because you measured the temperature at the beginning and the temperature at the end. So you can work out the specific heat capacity. Yay! How exciting. It would be a bit exciting, wouldn't it, to do it and see, then look up what the answer was and see how close you were, like how good your experimenting had been. Now, I read through all that on Tinternet, and I had some questions, okay? So step 1, take the mass of the 1 kilogram aluminium block. Why? It's literally a 1 kilogram aluminium block. Like, it says it on it. It says it on the box. Why are you taking the mass of the 1 kilogram aluminium block? If it seems obvious, can you check the wording? Can you have a little look at your... I mean, if you can, write that answer down, actually. Because I want to know if you get a mark at the end. If you think you can improve your mark, your answer. Be more specific. Put the thermometer in the other hole and record the temperature. Can you spot a problem with that? Can you think of a solution for that problem? And wrap the block in insulating material before you turn the heater on. Why? Why would you do that? I will let you have a little think, actually, because I think it would be quite useful. I know a lot of you will be like, oh, I could just think of it in my head. I don't need to write it down. But I wouldn't normally say, but because we're doing IGCSE physics, and if you do that, you probably will have to write stuff down. It's a good idea to write it down now, have a look at it, and think, is that definitely going to get me a mark? Even though I know what I'm talking about. Do I have to change a few little words here and there to be more precise? So, for example, if for question number 1, you've written, take the mass of the 1 kilogram aluminium block Y to double check. That is, it might get you a mark at IGCSE, but there's not a lot of detail there, is there? You don't have to write loads, you just have to be very precise. To double check isn't a very precise answer. To double check what? You've really got to imagine that the examiner has no idea what you're talking about. Take the mass of the 1 kilogram aluminium block to double check you haven't left the oven on? To double check you haven't left the back door unlocked? Double check what? Wrap the block in insulating material. Why? So heat doesn't escape? Where's it going to escape to? Should we go through it? Yeah, you do take the mass of the 1 kilogram aluminium block to double check the manufacturer's label is correct, or to check it actually is 1 kilogram. Because quite often you'll find that it's not, it might just be a little bit heavier or lighter, and obviously you want to be really precise if you're doing the more precise that your numbers are, the more accurate your final result will be. Put the thermometer in the other hole and record the temperature. You might be measuring the temperature of the air, right? Because there's air moving in and out of that hole all the time, because air particles have got a lot of energy. The solution that I've seen most to that is fill the hole with water or oil. Oil is the most common one, because the oil won't sort of circulate around the hole like the air will. It'll stay put. So the oil and the thermometer, I suppose you might want to say put some oil in and then leave it so that the aluminium and the oil are the same temperature. But yeah, just sort of creates a better seal. And wrap the block in insulating material so that all the heat is I should have maybe put all the heat from the immersion heater. So all the heat from the immersion heater is transferred to the block, not the surroundings. Oh, that's a good answer, isn't it? Okay. Well done if you've got that far. It's a very dense lesson, that one. I've got a little puzzle for you. Do you remember the second glass of water that we put to one side at the beginning of the lesson? Do you remember? Oh, we better use that, haven't we, before we go? So get the other glass of water, the one that hopefully you haven't put your hand in. I didn't say, did I, to have them both the same amount, to have the same amount of water in both. I want you to have less water in one of them. So as long as you haven't had your hand in it, you might just want to drink it. Because staying hydrated is good. Okay. A bit faster. So you've now got 2 glasses of water. One doesn't have much water in, and one has more water in. Can you tell me, now we're at the end of the lesson, which one of these glasses of water has the highest specific heat capacity? Which one of these glasses of water has the highest specific heat capacity? The one that is nearly full, or the one that is nearly empty? Which one has the highest specific heat capacity? It's related to this question. We talked about how the equation for specific heat capacity is energy equals mass times specific heat capacity times temperature change. Does the specific heat capacity of a substance depend on its mass? Does the specific heat capacity of a substance depend on its mass? I think that's quite a difficult question. So the answer to the first question is, they've both got the same specific heat capacity, because it's specific. That's what specific in that horrible 3-word sentence means. Specific heat capacity is the amount of energy it takes to increase the temperature of 1 kilogram of the substance by 1 degree C. And they're both water. So water has a specific heat capacity. That's why we talk about specific heat capacity, because it wouldn't be very useful, would it, to talk about the heat capacity of some water and then a bit more water and even more water. We just want to know, we want to be able to compare like water to copper to iron. So we compare the same amount each time. So water has a specific heat capacity, and what is it, like 4,200 joules per kilogram degree C. And that's it. It doesn't change like depending on how much it is. The heat capacity does change. Like, you might have said the one with not much water in it because you were thinking that the one with less water in takes less energy to heat it up. And you would be absolutely right if you put both of these like over the same, exactly the same kind of candle flame. The one with hardly any water would heat up a lot faster, because you don't have, there's not as many water particles basically sharing the energy. So this one would heat up faster, but they've both got the same specific capacity. So yeah, it doesn't depend on mass. I thought that might catch you out because mass is in the equation, and quite often we talk about, you can tell what something depends on by looking at the equation, but it's a little bit like timing lots of people doing a 100-meter race to work out their speed. And then if one of them is a bit slow, being like, oh, well, I'll just change the distance. Like, you can't change the distance because it's a 100-meter race. So you need to have, distance is in the equation, but it's not, it's a bit like that. So well done if you got that. And also, if you didn't, then I'm really glad that I threw that in. So my final question is, have BBC Bite Size got it wrong? Okay, I occasionally go to BBC Bite Size for my sort of information, what you need to learn. And here is, it's GCSE actually, AQA, it's on the syllabus, about specific heat capacity. Here we go. It says, different materials require different amounts of energy to change temperature. The amount of energy needed depends on the mass of the material, the substance of the material, specific heat capacity, and the desired temperature change. Is that right? The amount of energy needed depends on the mass of the material, the substance of the material, and the desired temperature change. Is that right? Or have I written into them? It's fine, isn't it? It's totally fine because they're saying the amount of energy needed to heat up a thing depends on the mass and the substance and the desired temperature change. And that is correct. Yes. It's just that the specific heat capacity of a thing doesn't depend on the mass. All right. Very well done. That was marvellous. I'm going to go over to my Facebook page now and see if anyone has left me any comments. And then I'm going to go. So if you like things that I do on YouTube, and you're watching live, tomorrow at 9 a.m. I'm doing a all ages lesson about how telescopes work, which has been a real revelation for me actually, embarrassingly so. And then at 10:30 tomorrow we're doing a Lego store show about lizards and chameleons and geckos as well, which you're very welcome to come to. I better tell you how this is free because it's amazing actually. I've won an award. I've legit won like a proper medal because this is such a brilliant business model that I kind of made up. I mean, you helped a lot. Look, it's even got my name on it. How good is that? Because yeah, I've got a science degree and I'm trained to teach physics to A level, but I make all of my lessons completely free and accessible to everybody. Even the printouts are free. Yeah, which is brilliant, isn't it? But it does require people to pay me. I keep saying I'm basically like a busker. So buskers aren't like charities. They only do their job because people do throw the money, and you are throwing me money, and that is how I can do my job. So if you haven't signed up to support me with £5 a month, and you think that what I'm doing is worth £5 a month, you can go over to my Ko-fi page and sign up. You can cancel anytime. I send you really nice things to say thank you. You get especially nice things if you sign up now, actually. Magazines and glasses that show you all kinds of different cool stuff. Yeah, and it keeps me going. And it is my full-time job. So thank you very much. And oh yeah, it's in my it's in the description of this video, but it's also in my about section on YouTube, or click where it says sign up on my website. Click where it says sign up on my website, or just Google coffee data science. I've tried to put it in as many places as I can because my entire family's income depends on coffee. Now I've said that out loud, that sounds sort of scary, and I feel like I should work on some different income streams. But anyway, that's a different problem for another time. Edmund says the problem with putting the thermometer in the hole is that you would then not be able to see the numbers on the thermometer, read the temperature from it. That is an excellent point. That is a really excellent point. And that's all the more reason to put oil in, isn't it? Because then you could just kind of dip you'd have to have like a clamp stand holding the thermometer very carefully because it's made of glass, just dipping it into the oil, I suppose, so they could read it. Very good thinking. Hello, Bastian. Hello, Freya. Hi, Jacob. Hello, Rocklin. Hello, Casper. I was trying not to go higher, but I still went higher because I'm excited. Hello. And Kai. Oh, that's nice. And then Casper says, this lesson was good. Bye. All right, bye you. I'll do a quick refresh, but I think that's everybody. I'm going to go and, oh no, there's another one. There's another comment. Here's this comment. Oh, it's the Capybara Kids. Hello. We got our magazine this week. Yay. Thank you, Capybara Kids. Oh, thank you. That's so nice. Oh, that's so lovely. Thanks very much for that. Excellent. Well, I'm glad I refreshed then. Okay, you lot. Yeah, I'm going to go. I'll see some of you tomorrow, or I'll see you next week. Next week is our last IGCSE physics lesson about solids and liquids and gases. It's the end of the module. We're going to do about the Kelvin scale, which works out really well because we're doing astronomy in all ages at the moment, and the Kelvin scale really relates to astronomy, so that'll be fun. And then we've got 3 more lessons left, but they're sort of standalone lessons about electricity. We're looking at like solar panels and wind turbines. And then there's the half term, and then we've literally only got 1 module left. We're doing radioactivity to end. And that's it. So, yeah, I was just telling you my plans. Okay, now I'm going to go. Thank you for supporting me. I'll see you all soon. Bye.